We welcome you with much joy in the videos of Chapter 24 of Crystal Clear Electronics 2. Chapter 24 is the finale of the second season, where we will implement a complex task using the examples we have learned in the curriculum. In doing so, we will see how the knowledge we have learned so far can be integrated into a larger system and made to work there. The lead presenter of the chapter, for your surprises, is Szabolcs Vereb, and I am Péter Pácsonyi, Chief Engineer of the BME Formula Racing team. Szabolcs, please tell us about the issues we're going to address in today's videos.
Well, I don't know about you guys, but when I take a shower, I somehow never manage to adjust the water temperature. It always gets either too cold or too hot.
I think you are not alone about this. I understand you can get a thermostatic faucet in the shops. Wouldn't that solve your problem?
Yeah, it would certainly do it, but I'm an engineer and I love a challenge. I hope you love challenges too. I was thinking that we could make a gadget that could adjust the temperature of the water by moving a valve, so that we could get the water temperature just right for us.
I would have preferred to see a full industrial water treatment plant implemented, but this will be a good first step. Just to be on the safe side, let's leave the option of manual adjustment, and we could also record the amount of hot water used on an SD card, so we can motivate ourselves to save some pennies.
Okay, let's make it happen.
The creation of a complex system can be broken down into several subtasks. These are usually carried out by a team of professionals, but for a simpler task, one person may be sufficient.
In general, the first step is to define the requirements that the finished system must meet. Then comes the design of the system, followed by the implementation of the system based on the plans. The prototype is then tested, and, after any faults have been corrected, the system can be installed and put into operation at its final location. The sequential order of the development steps that you heard may seem straightforward, but the situation is not always so simple in practice.
The simplest development model is the waterfall method, where these development stages follow each other in a strict sequence with no overlap between them.
It is easy to see that in practice, the final and complete specification is not always known. New requirements may arise during development on the customer's part, or the original idea may encounter some feasibility problem that was not foreseen during the specification.
This is improved by the evolutionary model. The development steps are repeated several times in a cyclical manner. The specification is prepared, and on its basis, the development and production of the prototype system is started. As new aspects emerge during development, the specification can be modified and development can start again.
In our water temperature regulator task, the complete, accurate, and feasible specification is known in advance, so we will not need more iterations, and we can develop the system according to the waterfall model.
The first step is to define what we need to perform the task. We want to control the temperature of the water flowing from a tap or shower. We already know from our lessons on control systems that we will certainly need some kind of sensor to measure the controlled characteristic and some kind of actuator to control it.
In our case, the controlled characteristic is the temperature of the water. To measure this, we will use the NTC thermometer described in the chapter on sensor calibration. As the actuator, we will use a valve that we can open and close to any extent we would like to with a brushed DC motor, just as if we were turning the valve on the tap ourselves.
There are many different types of valves, and we can always choose the right one depending on the field of use and requirements.
Perhaps one of the simplest designs is the so-called butterfly valve. A manually operated version is shown in this picture. It's basically made of a tube and a circular plate on a rotating shaft, which blocks the fluid from flowing through, thereby increasing the hydraulic resistance and reducing the amount of fluid flowing through the valve in a unit of time.
The butterfly valve's hydraulic resistance is small, and a small torque is required to move it, but it can only be used at low pressures. We have created a 3D printed butterfly valve model, which we will use when developing the software. The geared motor is connected to the valve shaft via a belt drive. This would be the valve's armature, and this is the plate that blocks the flow of the fluid.
A mixture of hot and cold water flows out of the shower. For the sake of simplicity, we will only intervene in the flow of hot water. The flow of cold water is considered constant. If the user wants the water as cold as possible, then we turn the hot water off completely. If they want it as hot as possible, we open the valve completely.
Once we have selected the components of the control loop, we will need a panel with the buttons and the display, through which the user will be able to set the desired temperature, see the actual temperature, and this will also contain the SD card where the water usage data will be saved and read back when viewing the statistics.
It should be considered whether the hardware that implements control and the one that provides the human-machine interface, or HMI for short, should be handled as one unit or rather split into two separate printed circuit boards. It is possible that the mechanical part where the valve and thermometer are to be placed is far from the human-machine interface unit. In this case, it is advised to split our system into two parts, otherwise long wires would be needed to drive the motor, read the encoder, and measure the temperature. It is also easy to run out of space where the HMI devices are placed, so the hardware that performs the other functions may be placed in the mechanical section containing the valves. However, if the system is not split into two parts, it may be easier to commission and maintain, and fewer components will be needed, so the overall system may be cheaper and simpler. For example, in the split solution, we would require 2 power supplies and 2 microcontrollers. For simplicity, let's assume that we implement the whole electronics on one common printed circuit board.
All the components needed to build the hardware have already been covered in the previous chapters. To drive the geared motor, we will use our H-bridge control panel. Since we need to be able to adjust our valve to different positions, we will definitely need an encoder. We will connect the NTC to the analog channel A0 of the development board via the breadboard and measure the water temperature using the analog to digital converter of the microcontroller. The potentiometer is connected to the analog channel A1. In manual mode, this will allow us to directly adjust the position of the butterfly valve.
The OLED display will show the current mode and the water temperature. In controlled mode, we will display the desired temperature. In manual mode, the current position of the butterfly valve. We will also need an SD card to which we can periodically save the amount of water used. The push buttons will allow us to navigate the menu system.
In the next video, we will design and implement the software that controls the system. See you there.
Bye.